Lecture 1-4, Atoms and the Periodic Table. Dalton's Atomic Theory, 1807. Dalton proposed that matter is composed of very small particles that he called atoms. The atom being the smallest unit of an element that can participate in a chemical change. An element consists only of one type of atom, which has a mass that is characteristic of that element and is the same for all atoms of that element. Atoms of one element differ in properties from the atoms of all the other elements. And finally, a compound consists of atoms of two or more elements combined in whole number ratios. And in a given compound, the number of atoms of each of its elements are always present in the same ratio. There are three subatomic particles in each atom. The first is the electron. It has an extremely small mass and a charge of -1. The next two particles are in the nucleus. The proton, having an atomic mass of approximately 1 and a charge of +1, and the neutron, which has a charge of 0 and an atomic mass of approximately 1. The masses of the proton and the neutron are almost the same, with the neutron being slightly heavier. Both the proton and the neutron are approximately 1,840 times the mass of the electron. Therefore, most of the mass of an atom is located in the nucleus with the protons and the neutrons. The atomic mass unit, or AMU, has a very small mass of about 1.66 times 10 to the minus 27 kilograms. The atomic symbol has three components. The first part is the elemental symbol, which gives it its characteristic letter. The symbol is always a capital letter followed by lowercase letters, either one or two lowercase letters. Then in the upper left-hand corner is the mass number. The mass number is the total number of protons and neutrons in the atom. So it's a counting number and is a whole number. The atomic number, Z, down here in the lower left-hand corner, is the number of protons in the nucleus and is often left off the elemental symbol because the symbol and the mass number both correspond to the same element. And down here we have two examples of it. The first one is hydrogen 1. It has one proton in the nucleus, no neutrons, for a total mass number of 1. And that number also appears in the lower left-hand corner because it's atomic number 1. In uranium-235, we have 92 protons and 143 neutrons, giving it a total mass number of 235. The one thing that Dalton didn't understand was the concept of isotopes. He supposed that all the elements had the same mass, but what we find in the atoms is that most of the elements have differing numbers of neutrons in them. And these differing numbers of neutrons gives us different masses. And the mass that we see on the periodic table is an average of all those masses. The first example is hydrogen. Hydrogen comes in three basic isotopes: hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 has one proton, no neutrons. Hydrogen 2 has a proton and a neutron, giving it two elements in the nucleus. It's also called deuterium, and it's also given a symbol of D. Hydrogen 3, or tritium, often given a symbol of T, has two neutrons and a proton in it. It's so unbalanced in neutrons to protons that it's actually radioactive. and slowly converts to helium-3 over years of time. Also below, we have two different major isotopes of uranium, uranium-235 and uranium-238. Again, the difference in these is the number of neutrons in the nucleus. The other thing to stress that I didn't on an earlier slide is that in the neutral atom, we will not see a charge, which is generally in the upper right-hand corner when we look at the symbol. When there is no charge there, the number of protons equals the number of electrons. So let's look at carbon-14 and count the number of protons and neutrons. Carbon is element number 6, and carbon-14 has 14 total protons and neutrons. So the number of protons is 6. The number of neutrons has to be 8, because 14 minus 6 is 8. And the number of electrons in a neutral atom is going to be 6 electrons. Well, let's look at this also for boron 11. Boron is element number 5. So it has 5 protons and 5 electrons. And the difference between 11 and 5 is 6, so it has to have 6 neutrons. Average atomic mass. Molecular mass can be measured with a mass spectrometer. In this picture is a replica of J.J. Thomson's third mass spectrometer, used to measure the masses of gases. The atomic weight that you see on the periodic table actually represents the average mass of the naturally occurring isotopes. It is called a weighted average because it's not a direct average, where you take 1 and 1 and add them and then divide by 2. For example, the average mass of carbon is 0.9893, which is 98.93% natural abundance, times 12 atomic mass units. Added to that is the other 1.07%, which is carbon-13, which has atomic mass of 13.003355 units. Putting those together, the average atomic mass is 12.01 for carbon. Again, here's an example of the two major isotopes of copper, copper-63, with an isotopic mass of 62.929599 and a natural abundance of 69.17%, and copper-65, which has an isotopic mass of 64.927793 and a natural abundance of 30.83%. So what we do is we take the first isotope, copper-63, and multiply it by its natural abundance, and add to that the isotopic mass times the natural abundance of copper-65, adding them together and putting it to the appropriate number of significant figures, we find that the average isotopic mass is 63.55 atomic mass units. The periodic table. The modern periodic table is composed of 7 rows, also called periods, and we find that the properties of the elements tend to vary in a regular fashion across a period, with some exceptions. A group or a family are elements located in the same column. For example, group 1, over here, these yellow colored elements are called the alkali metals. They have similar properties to each other. Way over here on the right-hand side are the noble gases, which again have a particular set of properties as noble gases. Other groups have particular names that we will look at shortly. However, you must note that these two rows down here at the bottom correspond to excerpts from row 6 or period 6 and row 7 or period 7, and do not have corresponding group numbers. Cerium, for example, is not in group 5. Cerium occurs here in the gap between lanthanum and hafnium. That is, it's between groups 3 and 4, not having a group number in and of itself. The period 6 excerpt is called the lanthanides, and the period 7 excerpts are called the actinides. So here are those groups that I was talking about. Group 1 are the alkali metals, except for hydrogen. Group 2 are the alkaline earth metals. Jumping over to group 15, these are the pnictogens. Following them in group 16 are the chalcogens. Group 17 are the halogens, and group 18 are the noble gases. Groups 1 and 2 combined with groups 13 through 18 are also known as the main group elements or the representative elements. And when we look at periodic trends, we're mainly going to be looking at the main group elements, because the transition metals and the intertransition metals, that is the actinides and the lanthanides, don't always have a periodic set of trends that follow the pattern that we see in the rest of the periodic elements. The transition metals are those metals that occur between groups 3 and 12 inclusive. However, zinc, cadmium, and mercury, if you'll notice they're slightly highlighted a different color, kind of an orange color, aren't considered traditional transition metals simply because their chemistry is more akin to only losing 2 electrons from their outer shell, and so they have a similar chemistry to each other and don't have chemistry similar to the rest of the transition metals, which have multiple ionic charges. Then the intertransition metals are those lanthanides and actinides that are pulled out of the periodic table from group 6 and group 7, and they are at the bottom of the periodic table. So let's identify the 5th period halogen. Let's go to period 5. Here's period 5. Go all the way across. Here are the halogens, group 17, and the 2 lines intersect at iodine. So the 5th period halogen is iodine. Identify the 3rd period alkaline earth metal. The 3rd period is here, going across. The alkaline earth metals are group 2, coming down. They intersect at magnesium. Sometimes the period number is a bit confusing because there are only 2 elements in the first period, and it's often forgotten when looking at and counting down rows. The best way to remember which period you're in is to look at the far left-hand side of the periodic table, where there's usually a number corresponding to the period. The periodic table is also grouped into metals, metalloids, and nonmetals. The metals comprise most of the periodic table and have properties such as conduct electricity fairly easily, conduct heat fairly easily, are malleable, can make them into wires, bend them, and such. The nonmetals however, do not have such properties. They have a variety of different properties. Some are gases, some are solids, some are liquids, and they don't conduct electricity very well, and they don't conduct heat very well either. The metalloids, this section in yellow here, comprising boron, silicon, germanium, arsenic, antimony, and tellurium, are called metalloids or semiconductors. They have physical properties resembling metals and chemical properties more typical of the nonmetals. Physical states of the elements. Most of the elements are solid. However, there are two liquids to note. Mercury is a liquid at room temperature, and bromine, over here in the halogens, is a liquid at room temperature. And finally, there are gases. Of course, all of the noble gases are gases. And then hydrogen being the lightest of the elements. Nitrogen, oxygen, fluorine, and chlorine are the other four gases. Hydrogen, nitrogen, oxygen, fluorine, and chlorine are diatomic gases. Bromine is a diatomic liquid, and iodine is a diatomic solid.